Hello everyone, I'm Prakirt. I'm presenting on heavy traffic performance of low complexity scheduling algorithms in data centers. This is a joint work with my advisor Siva, Theja, Maguluri. Let's first look at what is an input queue switch. An input queue switch is the primary device used for the exchange of data in the data centers. A switch consists of n input ports and n output ports. The system can be represented by an n cross n matrix where each element represents a queue. Due to architectural constraints of the switch, you can only serve one queue in each row and one queue in each column. Thus, the possible schedules are permutation matrices. The schedule in time slot k is represented by the vector sk. By convention, we assume that the schedule is decided before the arrivals come in. The weight of a schedule is the sum of the queue lengths that are being served. In this example, the weight of the schedule is 6. After the schedule is decided, the arrivals come in and join the queue. The arrival process is denoted by the vector AK. Once the arrivals join the queue, you serve the customers according to the chosen schedule. Lambda denotes the arrival rate. The capacity region of this system is given by the set of lambdas for which the row sum and the column sum are less than 1. Lambda can be represented as 1 minus epsilon times nu, where nu is on the boundary of the capacity region, which means that the row sum and the column sum for this vector nu is exactly equal to 1. Epsilon is known as the heavy traffic parameter. We say that the system is in heavy traffic if epsilon is very small or close to 0, which is same as saying that lambda is very close to the boundary of the capacity region. The system is said to be in uniform traffic if all lambdas are equal. In such a case, the lambda vector is given by this form. Now, some algorithms that we present in this talk are stable only under uniform traffic. They're not stable under the whole capacity region. For the simplicity of this talk, we will assume that the total variance is of order n. Now, this is just an assumption for this talk. It is not necessary. This can be easily relaxed. The most popular algorithm in switch scheduling is MaxWeight. Now, as the name suggests, MaxWeight chooses the schedule which has the highest weight. Now, in this example, that schedule corresponds to the one in which you serve the queues on the diagonal, and the weight here is 10. If you use the textbook Hungarian algorithm, then the complexity of this algorithm is of order n cubed. In 2006, Maguluri showed that for MaxWeight, the scaled mean sum queue length is of order n in heavy traffic. Now, this is true for a very high complexity algorithm. In our work, we extend this result, this heavy traffic result, to several low complexity algorithms. We say that an algorithm is heavy traffic optimal if it has same heavy traffic limit. This limit is same for that algorithm as it is for MaxWeight. This table kind of represents the summary of the work we have done in our paper. We show that there are several classes of algorithms for which the system in heavy traffic optimal. Our results show that random scheduling is not heavy traffic optimal. But there are several algorithms which are slight improvement of random, like power of D and random D flip, which are heavy traffic optimal. But they are not throughput optimal. So we show heavy traffic optimality for these two algorithms only under uniform traffic. We also consider several algorithms that were presented in past literature. We present two new algorithms, namely random D flip and D flip, Although we present the performance results for random deep flip, we don't know any performance results for deep flip. Due to lack of time, we are only going to look at 4 of these algorithms in this talk. First algorithm is power of D. Power of D is a very simple algorithm. In every time slot, power of D samples exactly D schedule out of n factorial possible schedules and chooses the one with the highest weight. The time complexity of sampling one schedule is order n, and calculating its weights is also order n. And as we are doing it for D different schedules, the time complexity of the overall algorithm is order dn. Now, power of D is not throughput optimal, but we know that it is stable under uniform traffic. So we show that under uniform traffic, power of D is heavy traffic optimal, which means that the scaled mean sum queue length for power of D under uniform traffic is order n. Next algorithm is pick and compare D. Pick and compare D is one-step modification of power of D. So in pick and compare D, you sample a schedule using power of D, you generate a schedule using power of D, which is S here, and then you compare it with the schedule you used in previous time slot, SK minus 1. And you choose the schedule which is better among these two. Now, this comparison step not only improves the performance quite a lot, it also makes this algorithm throughput optimal, which means that pick and compare D is throughput optimal, even though power of D is not throughput optimal. Note that this comparison step has a complexity of order n because you are only comparing the weight of 2 schedules. So this comparison step does not affect the overall complexity of the algorithm. So the complexity of pick and compare D is only order dn. We show that under general traffic, pick and compare D has same heavy traffic performance as MaxWeight. So pick and compare D is heavy traffic optimal. Next algorithm we look at is random D flip. Random D flip is one algorithm that is newly presented in this work. Let's first look at what we mean by a flip step. Suppose you have a given schedule like this. Now you choose exactly 2 queues which are being served in this schedule. What you do is you flip the service on those 2 queues. So if you're serving these 2 queues, you start serving these 2 queues. Note that this gives you a valid schedule, which is in this example is this one. And then among these 2 schedules, you compare the weight. Now, to compare the weight of these 2 schedules, you don't need to calculate the weight of the whole schedule. You can compare the weight by just comparing the queue lengths of these 2 queues and these 2 queues. And in this example, this queue has a weight of, these 2 queues have a total weight of 5, and these 2 queues have a total weight of 4. So you pick this schedule over this schedule. That's a flip step. In random D flip, you generate a random schedule at the beginning, and then you apply flip step D times recursively. Now, the complexity of this algorithm is order n plus D, where order n comes because you're generating a random schedule, and D comes because each flip step is order 1, and you're using D flip steps. So we should now random D flip is also not throughput optimal. So we show that under uniform traffic, it is heavy traffic optimal. So the final algorithm we present is D flip. In D flip, D flip is pretty similar to random D flip. So what you do in D flip is that you implement flip steps D times on the schedule you used in previous time slot. So instead of generating a random schedule, you just use the flip steps directly on the schedule you used in previous time slot. Note that as you're not generating any schedule, any random schedule, you only have to do computations for flip steps. So the complexity of this algorithm is only order D, which is very low. It can even be lower than order N. Now, we don't know any nice performance result for D flip as of now. But we can show through simulation that it performs pretty good. In this plot, we compare D flip with pick and compare D. We know that pick and compare D is throughput optimal. Also, it is heavy traffic optimal. But as you can see in this simulation, D flip performs much better than pick and compare D. So our conjecture is that there must be some nice theoretical results for deep flip, although we haven't shown that in this work. So we looked at several algorithms. Mostly we looked at power of D, random D flip, pick and compare D, and D flip. There are several more algorithms which were presented in past literature that we didn't look in this talk. In fact, there is a whole class of algorithms which are not included in this table, but they're also heavy traffic optimal according to the results presented in our paper. That's the end of my talk. Thank you. Here are some of the references that can be used for this talk. The top one is the paper that we have. You can find all the results in that paper. And in other references, you can find the reference for the algorithms that were mentioned. Thank you.